So, first thing we're going to do. First thing we're going to do today. The lab yesterday, the thing I wanted you guys to discover was the following. And some of you noticed it, and some of your numbers turned out this way. When you plotted your diameter on the x-axis and your circumference on the y-axis, you had a bunch of data points, and then you're supposed to, again, put your best fit line through it. Then pick 2 points on that line. They could have been your data points or 2 other points, and then find the slope. And if you notice, slope, remember, is delta y over delta x. But in this case, what is your y-axis here? What represents your y-axis, the circumference or the diameter? I heard both. Which one is it? Look on the board, Enrique. It's the circumference there. Be careful. Okay, the y-axis is circumference right here, where the x-axis is diameter. So this delta y is really talking about a change in circumference. You know how this is really the y-axis? It's really like saying delta c. And this is really like saying, instead of delta x, delta d. Okay? And that's the same thing, really. It is. So whatever your labels are, that's really what your slope is. Well, if you think back to geometry, in geometry we're told circumference equals pi times diameter. Solve for the value pi here. How do I get rid of that d next to it?
Divide it.
Divide it, don't I? And when I divide it, if I divide both sides by pi here, or by d here, we're going to see that the value pi is really the ratio of the circumference to the diameter. So when you did your slope a minute ago, take a look back at your slope. Wasn't it delta c over delta d?
Yeah.
And look down at the bottom now. This is delta c really, this is really delta d. So the value that you really wanted to get from the slope was pi. And a lot of people got close to that, some had a little bit off. I saw some values of this that were like 3.2. I saw some that were 4.5, which was a little bit higher. I saw some that were like 2.8. I did see one person with 3.15. Okay, and what is pi though? Estimate? 3.14, 3.15, right? Estimation. We know from yesterday and from ever, pi goes on forever because it's irrational. But the whole goal of yesterday was to determine experimentally how pi was developed over a long time. Because it wasn't just a number that somebody made up. The question that was always posed was, if I know the diameter of the circle, how can I figure out that circumference? So enough scientists took data and they plotted the circumference versus the diameter, realizing that the slope was this value of this irrational number pi, 3.1415 and so forth and so on. So the goal yesterday was to gain a value or to get a value here of around 3.14. Now, that might not have happened. Can I get a show of hands? Was anyone's range in the 3? Did anyone get 3 point something? 1 in here, 2 in here, got 3 point something? Anybody getting a 4 for their slope? 4 point something. Okay, what about 2 point something? How about this? Tell me what your slopes were to make this easier then. Okay? Well, what did your groups get for your slope?
Don't really know, actually.
Did you get to do it or no?
No.
You got to finish that and check. Ebony? 3.6? Okay. 3.6. What about over here? What did you get when you calculated your slope? So when I collect this in about 30 seconds and everybody gets like 50 on this for a grade, you're going to understand why now, right? You had one assignment last night, guys. One assignment. That was it. You had no other homework. You're supposed to just finish this up. Rosie? 3 point what? 75. Thank you. The goal was to get 3.14. Again, that was the goal here. If you didn't do the work, you're not accomplishing anything. You're losing yourself here. Okay? If you guys don't want to do work, find another school to go to. It's getting old now. Okay? You want to be here? Do your homework. You had one assignment last night. One assignment to finish that worksheet. That takes a whole of maybe 5 minutes to calculate slope. It's really pretty sad to think about. Unfortunately, that's going to start us today. Let's go into the lesson now. We're going to look today, and we're going to continue with end behavior. We're going to continue looking at this, and we're going to look at a new example. Yesterday, or 2 days ago when we looked at this, we talked about examples when the degree of the denominator was equivalent to the numerator. We looked at that leading coefficient. We looked at each of those. So to think back, we were talking about where the leading coefficient for these problems from the other day looked like this. We just said, let's take 2, let's take the 8 here. 2 over 8 is 1/4. So we got a horizontal asymptote of 0.25. That was from the other day. Now today, we're going to start looking at the second case. Okay, the second case. where the degree of the numerator is less than the degree of the denominator. It's less than. For this example, I can see here, and this is the tough part for this one. What's the degree of the numerator actually?
0.
Why is it 0, Marcus?
Because it doesn't have a variable.
Absolutely. There's no variable there. So there's no exponent to look for. Remember, in case you're forgetting, the degree is the highest exponent. The highest exponent of the function. So for the numerator, there is no highest exponent. So the numerator's degree happens to be 0. The denominator, what's the exponent here though?
1.
There's a 1 there. Again, it's really x to the 1. So the degree of the denominator is really 1. Now, if you go back and turn back to your table, please, from the other day, the one where we filled in all those data values and looked at the end behavior. So we had the table with the gray columns on the sides, and we put in all of our data in the middle. Okay, and then we filled that out. We came up with some conclusions. On the back of it, we made our conclusion. What was our conclusion if the numerator's degree was less than the denominator's? Less than the denominator's. What was the conclusion we made for that one?
The end behavior goes to 0.
Very good.
And there's a horizontal asymptote.
Very good. Again, end behavior goes to 0, and there's a horizontal asymptote at 0. Well, how do we work that out? Let's go ahead and take a look now. So, come on. There we go. So this is the degree of the numerator, and the degree here is 0 because there's no exponent, but the degree here is 1. The degree of the denominator is simply 1. So remember, degree is the highest exponent. If there's no exponent, like the top part, it's just 0. Okay? So what we want to do today is look at infinity notation, like we did last class. Remember when we plugged in the infinity and we dropped off that other term? We called it negligible, or what was the other word we used? Somebody else came up with the other word. I used negligible, but someone else used another word. What was the word that we used the other day? Anybody remember? Yeah, insignificant. That's it. Very good, Rose. Insignificant. We said the other day that if we plug infinity in, so go ahead and look at this function. Let's plug infinity in and see what goes on here. This is what we get. Now, who remembers what the example was? What did I say? Who's the rich person that we use as an example?
Only you know.
Bill Gates, right? Bill Gates. And we said, if Bill Gates has, we know how much money, or we don't know how much money, but we know he has a lot of money, let's say, right? Billions of dollars. If Bill Gates had $1, and somebody asked him for $1, it shouldn't mean anything to him, right? What's $1 when you have billions of dollars? So, in this case, was it $20? Thank you. In this case here, I've got infinity right here in my denominator. And I see this -1 thing. I see this -1 here. The -1 has no effect on my problem, really. Again, the -1 is insignificant or negligible. Because if I've got infinity, it's this huge number. If I take away 1 from infinity, it doesn't do anything, really. So we say that this goes to 0. Remember, we're not canceling it. We're saying that it goes to 0. So whenever I have infinity, if something is next to it that is not as powerful, I ignore it, really. So what am I left with, really? I'm left with just 4 over infinity. Now, this can be a little bit confusing to some students, and I'm going to try to explain to you with an example how to think about this. So, who likes pizza? Everybody pretty much, right? You all like pizza? All right. You're allergic to it? Sorry. Okay. So imagine, let's say, Enrique, Carol, Juan, and Brian, okay? The 4 of them are in the class, and they decide to order a pizza after school, and they share a pizza. There's 4 of them now. So if they share a pizza, they cut it into 4 and each get a slice, right? So they cut it into quarters. Now, let's say 5 more people come in the room, or 4 more people come in, and they say, oh, I want pizza too. So now there's 8 people. So now you have to cut it into 8, right? So now there's 8 slices. But now look around you. There's like, what, 15 of us in here? So what if we have to cut it into 15? What happens to my slice? Does it get bigger or smaller? It gets small. Be careful, I'm cutting it. Normally I have 8 slices for pizza, but I want to cut it into 15 slices. So they're going to be smaller each of them, right?
They're like bite size.
They're like bite size. Very good. So that would be quarters, the first scenario. Then if we had 8 people, it would look like that. Then if we had 15, it would look a little weird, but let's say 16. If there were 16 people, I have to cut each of those in half now. And then my slices get smaller. What happens though if there's like 50 people? How are we going to split a pie? What's everybody going to get? For 50 people, what's everybody really get? Like a little over what? like a little piece, right? Pretty much. I mean, we have to then cut this more and more and more and just keep slicing it up. Eventually we'd have to cut it what? We'd have to cut it maybe this way then, and cut this part and make a lot of different cuts. And we'd have 50 pieces. But what's happening to those pieces? They're getting smaller, right? Yeah. Now, what if I had 1,000,000 people and I had one pizza? Everyone's literally going to get what? Like right? The smallest value possible. And as we think of acids, very good. So here, if I take one pizza, or even if I take 4 pizzas, and I divide it by an infinite amount of people, theoretically, everybody's piece becomes smaller and smaller and smaller and smaller until you have nothing left, really, right? There's no piece of pizza left. So this is approximately 0. Again, think about it this way. If I take a number, anything over infinity, if you have any number over infinity, it basically just goes to 0. Okay, and that's where the rule, and that's why I'm putting approximation. Because theoretically you have something, right? If I take a pizza and I cut it into 1,000,000 pieces, everyone's going to have something, but it's going to become so small that it's pretty much nothing. Okay, so when you divide by something like infinity, you get 0. You get 0.
So wait.
Okay? Not working? Lower your headphones. Is that coming out of the headphones or is that coming out of the headphones? So here, again, when I divide a number by infinity, it's like saying I'm dividing it by so much that there's nothing left. There's nothing left. Okay? Same thing about it. Imagine you have $1. You have $1 in front of you. And 1,000,000 people want to split that $1. Everyone's going to get like a fraction of a penny, aren't they? If I had 100 people, everybody gets a penny. Easy. There's 100 pennies or $1. But if I have 1,000,000 people, then everybody gets like this little piece of a penny. If it keeps getting bigger and bigger, if I keep having more people split up, eventually you're going to get nothing. You're not going to get anything. I mean, what's 0.0001 pennies? That's like no value, right? So it's approximately 0. So that's the idea here. So if you look back to your second case, Jose, you started the class by saying when the denominator's degree here happens to be bigger than the numerator's, we say that there's a horizontal asymptote, and we said that was at y equals 0. Well, where does that come from? That comes from right here. The fact that it becomes 0 as x goes to infinity, or it becomes 0 as x goes to negative infinity. So whenever you have a degree where the numerator here is less than the denominator, we can say that there's a horizontal asymptote. Where is it located? At y equals 0. At y equals 0. Follow-up question for you. What does y equals 0 look like on a graph? What does that look like? Intercept is not the word we want to look for. Axis for short. When y equals 0, how do I graph that? Because remember, it's horizontal because it's a horizontal asymptote. So we know it's going to be horizontal. Where is it? On the what axis? X-axis. Let's think about this. Here, this is the line y equals maybe 2. This is the line y equals 1. This is the line y equals negative 1. This is negative 2. But where's y equals 0? It is the x-axis. So, to me, I would never use the word x-axis if I were inventing math. I would say the y equals 0 line. Because it's just another way to confuse you. Why did we come up with the x-axis? What does it mean? It just means that that's the x-coordinate. But really, how do you define the x-axis with the line y equals 0? That's what the x-axis really means. So in these cases, with this problem, what I want you to do now, take out your calculator, please. For some reason you don't have yours, share with a neighbor right now. Go ahead and graph this in y1. And remember, you need parentheses around it. You need parentheses around it. So y equals, go to your y equals, and graph 4 over the quantity x minus 1.
Does everything have to have a parenthesis?
Whenever you have a numerator and denominator, I would be safe and put them both in parentheses. Really, you don't need the 4 in parentheses because it's by itself, but I would personally always be safe and put parentheses whenever it's a fraction. So go ahead and graph it, please, yeah? We got 4 over x minus 1. So I'm going to go into my y equals. I'm going to go ahead and type in 4, whoops, parentheses, 4 over x minus 1. Okay, 4 over x minus 1. Okay, graph, please. Oops, where's my line? There it goes. And what you're going to notice is this. Your horizontal asymptote, as we said a minute ago, occurs at the line y equals 0. And take a look. This graph, it wants to get closer and closer, right? That's why it's called an asymptote. Same thing over here. This part of the graph gets closer and closer, but it never is going to touch the line. It's called an asymptote. So when you're doing your homework tonight, when you're doing your homework this weekend, when you do these problems, you get an answer. Don't just get an answer. Please draw on your paper what it looks like on your graph so that you can verify that your answer makes sense. That it makes sense.
Mine came out different.
Did you put parentheses around it exactly like I did?
I did. And it came out different.
Hit zoom 6. Always hit zoom 6 to start if it looks different.
I get it.
Do you have anything else in the y equals?
He had 0 in his y equals 2.
That doesn't matter, it's
It
fine.
doesn't.
No, it doesn't.
0 is what you actually should have, because that's the horizontal axis. Here, let's see. It's because you're zoomed in.
I'm right.
Again, hit zoom 6. Hit zoom 6, please.
They're not supposed to be aligned.
I'll explain that in a second. Hit zoom 6 and you'll see the general shape. Some of you, depending on the model of the calculator you have, might have a vertical line right here. Does anyone else see that? Okay? That's what you have, right? All that's showing, remember the vertical asymptote we talked about last concept? Some of the calculators show a vertical asymptote. That's all that is. Okay? Again, the vertical asymptote for this problem occurs at x equals 1. Because if I put a 1 in right here, it becomes 0, doesn't it? And remember, the vertical asymptote is what makes that 0. So at x equals 1 here, you have a vertical asymptote. But what we're focusing on today is the horizontal asymptote, y equals 0. Okay? That's what we're focusing on. But you might see a vertical asymptote there based on your model.
Would this ever occur? Vertical and horizontal?
What do you mean, does it occur?
Like,
Will it show up for horizontal also?
yeah.
I don't know. Try it, but don't use this function. Use a function that has the same degree. So go back to the other examples we did. Example 1 and 2 of concept 44. Try to graph those and see what happens there. Okay? All right. With that said, I want to take a look at the next example here. Let's take a look at this one. It's a little bit more complicated because it's no longer linear. You have a quadratic denominator and you have a linear numerator. So please start by listing the degree. What's the degree of the numerator going to be?
1,
And the denominator?
2,
Why?
because it's the highest.
Highest what?
Exponent.
Very good.
Right.
Take a look at what I circled there. The exponent here is really 1. Because it's negative 5x, x is to the 1. The exponent here is really 2. So for this kind of a problem, we see again that the degree of the numerator is less than the degree of the denominator. When that happens, our end behavior goes to 0. It goes to 0. So we clearly have a horizontal asymptote at y equals 0. So go ahead, please, and graph this one and take a look. Okay, I'll draw a sketch up here, but I would like you guys to graph what it actually looks like. And please don't forget your parentheses. Very key. It's negative 5x squared. I'll graph it while you're doing it also. Or negative 5x rather. Divided by 1, 4, negative 2. X squared plus 4x minus 2. So that's what you should have in your y equals right now. Go ahead and hit graph on yours, please. I'm going to postpone mine for a second so you can see. Go ahead and graph. Yes, and that's going to look weird. That's what I want to talk about. It's going to look a little bit funky here.
I just said error. Wait.
You might have used the minus sign instead of a negative sign. Hit go to. When it says error, hit go to.
Right.
You have to put a negative sign instead of a minus.
Ho, wait. -2 or -2?
It's right up here. Hold on. I think you put a minus sign here instead of a negative.
Nah, I put negative.
Okay, then maybe you put a negative instead of a minus over here.
I put minus.
And it's still giving you an error? Hit go to. Where does it bring you to?
Look.
Hit, oh, first of all, it's negative x.
Right.
So you got insert, second insert.
Oh, second answer.
Press second insert. You want to insert, oh, get rid of the caps. Okay. Try to have second insert. You want to insert a parentheses, and parentheses or close.
Close.
Yep. Yeah. There you go. Now I graph. Alright, now you go to. No, you can actually run this there.
Go.
When you hit go to, it brings you to where the error is. You can hit pipe correct it.
Ah.
So, we got a lot going on here. Remember, this whole topic is called end behavior. Not middle behavior, but end. So I don't care about this right here. This middle portion of the graph, right now I don't care about it. I care about the end. And the end behavior still tells me that as I go toward the end, I'm going toward the line y equals 0. And as I go toward the end here, I'm also doing the same thing. So the ends are what matters. What happens in the middle, it's a little bit different. Okay, and we'll talk about how to work that out.
So, over to the left. How do you know the direction?
How do I know which direction? Start at the highest point, Mia, or start anywhere to the right of it, and go toward negative infinity. So I trace it toward negative, whoa, why isn't that working? I trace it toward negative infinity like that. So it's going toward the line y equals 0 here. I trace this one toward its end, which is positive infinity. This end is positive infinity, and it's going toward the line y equals 0. It's always the ends. So start in the middle, Mia, and work your way out. So start here and work your way out. Okay, again, end, that's the whole key. So both of these parts are going to y equals 0. How come again? Because the denominator degree happened to be bigger than the numerator, or because the numerator happened to be less than the denominator. Okay, that's our second case. So far what we've done here, from the first day, when the degree are equal to each other, we said the end behavior was the line y equals, and it was the leading coefficient over the leading coefficient. When the degree of the numerator was less than the denominator, like we just did, it went toward the asymptote y equals 0. Those are the ones that we've done so far, and you already have this. It's on the back of your paper that we did the table on. Okay, you have those two things already. When the degree of the numerator is bigger, though, we had this plus or minus infinity. And that was the one that looked kind of weird. So that's what we're going to really focus on now. So let's go ahead and take a look at this example. So this is case 3, or scenario 3, where the degree of the numerator is bigger than the degree of the denominator. Tell me, what's the degree of the numerator?
2.
Okay, the 2 there. Denominator?
1.
Because there's really a 1 here. So, clearly, the degree of the numerator is bigger than the degree of the denominator.
I mean, it has to be.
Okay? Bigger than the denominator. Here you go. Go get your board.
Look at what the drawer.
So this kind of a problem here. We see that the numerator is bigger than the denominator. So my ends are going to go off to infinity or negative infinity. But the question becomes, how does this actually work? And here's how I'm going to show you right now. Okay, again, the ends of this will clearly go off to plus or minus infinity, but we don't know which one's going to go where. To determine that, you need to use synthetic division. Think back to synthetic tables. If I have a synthetic table here, and I look at my problem here, this is really a division problem. When I did synthetic division, I started by putting my coefficients up top. So I start by taking the coefficients of 1, 3, and negative 4. Those went across the top. And does anybody remember what goes on the outside?
1.
It doesn't matter.
Oh, yeah, it doesn't
Which
matter.
one to use.
The first one.
That was if I was guessing, but it does matter here. I have to use my denominator. But be careful, it's not 1. Why is it negative 1? Do you remember?
Because it doesn't have the equal sign.
The opposite.
Here we're trying to figure out, this here, right, this is a factor. It's what we're dividing by. But we always test the roots. Remember the roots? So here you need to put a negative 1 outside. Again, so the process for this third case, is to be doing synthetic division. So you take the numerator, the 1, 3, 4 up here, you line those up here, 4 being negative. You take the x plus 1, and you remember that you need to do the opposite of this, which is negative 1. Okay? Whenever we're doing this synthetic division, it's always the opposite. Okay? Start by bringing down a 1.
When the numerator is greater than the denominator, we always have to do that.
Yes. Whenever the numerator is bigger than the denominator, we use synthetic division. Whenever this case, whenever the degree of the numerator is bigger than the degree of the denominator, if you look back up here with all this scratch that's on here, whenever one is bigger than the other, the top is bigger than the bottom here, you know you're going to have to use synthetic division. Start by carrying down your 1. Now how do we do this again?
0 first.
1 times 1
That's what I said.
is
Negative 1, so it's 3 is 2.
Okay, so we start by saying negative 1 times 1 is negative 1, plus the 3 gives me the 2 there. Then I say negative 1 times 2 is negative 2. Negative 2 and negative 4?
Negative 2.
Negative 6. Be careful there. And how did I write this? I started with x squared. So what did these all become then?
X plus 2 minus 6.
Again, this was x squared, so this becomes x to the 1. Remember, you reduce it by 1. Go back, think back into your memory. Okay? Think back to synthetic division, which is concept 30s. Becomes linear, because this is squared, and this is a 2. What about the 6, though? What did we call the 6, really?
Remainder.
Very good, remainder. So it's minus 6 over x plus 1. Remember the remainder there? This is why we learn this stuff, guys, so we can actually use it here. So the remainder here is just 6 over x plus 1.
How is
Now.
6 going to be in the remainder?
Because remember the last thing that was here? If this turned out to be a 0, we said it was a root. If it wasn't a 0, we called it a remainder. That's your remainder right there. Now, here's what I would like you guys to do. Please graph the original in y1. Are you guys talking about something I need to ask? Can we focus, please? I ask a lot. Please don't do that. Graph the original in y1, please. Graph the original in y1. Go to y2 and now graph this and see what happens. Okay? Again, graph the original in y1 and graph this in y2. Graph this line x plus 2 in y2. It should be diagonal. Very good. Because x plus 2 has a slope of 1.
So wait, you put x plus 2 first?
That's your original, right? You graph the original. Now graph x plus 2 in y2. I want you to graph this in y1. This is going to go on y1, this whole function up here, and this is going to be y2 down here. Graph them together and see what you see.
Go first.
Es una línea recta.
And if it doesn't look good, press zoom 6. You gotta change your first one. You gotta graph your new one.
Is this right?
See what's up there on the board? Ux, graph that. You want the original function we started with. Come on. Where's the original function? Right there.
Is that right?
It should be right here. It should be right there. The original function is x squared plus 3x minus 4 over x plus 1.
Still okay.
I can't tell you. What's up?
The original is the u of x at the top. And the new one is the x plus 2. The remainder, we're going to do a little close. Guys, ignore the remainder, please. Ignore the remainder. You're graphing the original and the new one. The original's at the top, right? You're only graphing clear. That's okay? At negative 6 over x plus 1, that's the original now, okay? Let's watch what the next one is. Perfect answer. Let's take it closer.
What are you doing? That's wrong.
I want you to see this stuff. There we go. Good. That's right. Good. Keep going. Okay. You don't. Did you put the who's this? All right. You also put the remainder in there, didn't you? Just grab the original.
Oh snap! Cause I saw that her too.
Now grab that.
I saw that her too.
Okay. Then you're gonna see that.
Don't ask me about the trap.
So don't call it horizontal or vertical. So here, many of you got this already, but this is what your graph should look like. Now, I'll make a suggestion to you guys. When you graph, here's what I would suggest. If you're ever going to graph more than one line at a time, go to y equals. On the second line, go down here and watch what I do. Go over to this. Move your cursor to hover over the line type. Move over to it, please. And then hit enter once. And you'll see it becomes a thick line. You see that?
Yeah.
So you can see the difference now in your graph. And now hit graph again. Because in a minute, the next graph's going to look a little bit funky. So please make that a different line, make it a little thicker.
Oh.
So when you then graph it, you'll clearly see what it looks like. You could hit enter again. If you hit enter again, you get this shaded thing. Hit enter again, you get another shaded. Hit it again, you get these little dots. There's all different shapes you can use. Okay, there's a dash one. See the dots there? See those dots? That's kind of like what I did with my graph here. That's what you would get there. So you can show a bunch of different ones.
When you can change the shading, but it doesn't mean like negative and positive.
It shades above or below, yeah.
But does it mean like negative and positive?
Mine's got spots.
Try it, see what you see.
Look,
Try it.
look.
Can you see the domain array? Like with the little
Technically you can, yeah. I mean, that would be like all the things above it. So then you can't see all the ones below it. But that's kind of like the shadow test. Yeah, that's exactly what it's like. The problem though is this, Rosie. The functions I gave you to me arrange, remember they're all like little pieces and stuff? You can't graph them. You
What is
can,
this
but
for?
it's not.
Look.
Yes, exactly. It would take you more time just to come up with the equations than it would to just figure it out on your own. So, here's what we do now. We call this, first of all, this line is y equals, what was it, x plus 2? Right? That was the asymptote?
No, X plus 1.
Plus 1 or 2?
Oh, wait, 2.
Yeah.
And this is called a slant asymptote. A slant asymptote. Because if you look at the ends of the graph, the ends go toward the slant asymptote. Look at this clearly. We're going to see here that this graph, as it keeps going to, as x gets bigger and bigger, as I move to the right, this gets closer and closer to the slant asymptote. As x gets less and less, this gets closer and closer to the slant asymptote. So on this end, it's going toward negative infinity, because it's going down. But what about on this end? It's going up, so it goes to positive. What about right here for this portion? This is actually going to negative, and this is going up to positive infinity. Because these are lines, they go on forever. Remember that. Okay, these are really lines or curves, they go on forever. So, remember when we did the experiment, when we did the data table, we got plus or minus infinity. We said we don't know which one it'll be. We can't really tell. Now we can tell. We can tell that this side goes to positive infinity, and that this side goes down to negative infinity. How can we now tell that from our slant asymptote? From our slant asymptote. Let's do another example of a slant asymptote. Have it again. By using synthetic division, we came up with this asymptote. By looking at the graph, I follow the graph as x goes to the right. As x keeps going to the right, y keeps going up, doesn't it? As it keeps going up, it means positive. On this side, though, y, as x goes to the left, y keeps going down, 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 down further, which gives you the negative. So this is what tells us which way it's going, based on the slant asymptote. Okay? Based on the slant asymptote. Let's try another one. Let's try g of x equals let's try this one, please. Start by using synthetic division. Make your synthetic table. Find your slant asymptote. Ignore your remainder. I'm going to explain in a minute why we can ignore the remainder. But just for now, ignore it.
So we would just bring down our last.
Oh, you say sure. You do like that, girl. You ain't reaching out that.
Woo!
So wait, you just ignore 3? So your first number is 1, right?
I only got one line, Mr.
It's 5. Oh,
Mr. Howell.
Guess what?
I missed like 10 seconds, right?
It's working.
No, I'm just kidding.
What is it? I'm saying inside the book. Just the first number, 3 or 1.
There's only one line to cut. Oh, you have to do the other one.
And I'm gonna hit it.
So far, so good? Everybody got that part out? What goes on the outside?
I got my
Negative 1.
So what's 17 times 5?
Remember, the opposite of whatever this is, Jose.
Oh.
Whenever synthetic division occurs, you do the opposite of the factor in the denominator. Bring down to 3. 5 times 3 is? 15 plus 2 is?
17.
5 times 17?
85.
85 minus 4?
51. I mean.
Now, does the 81 even matter?
No.
Why? The 81 is what again?
Remainder.
And we said ignore the remainder for now. I'll explain why in a minute. So I rewrite this now as 3x plus 17 plus 81 over x minus 5. But again, I'm going to ignore this for now, and we'll explain why in a minute. Go ahead and graph this with your original. Again, graph this with your original. Sure. So I'm going to take the original and graph it with this together. And if you see it for this kind of a graph, you might want to zoom out to make it look a little better. To see actually what's going on there, you might want to zoom out. Press zoom, then hit zoom out, then hit enter. The original function, that was circling because I was talking to Jose about that. And then the part here, without the remainder.
Yeah, so you hit me again. Like I said.
It should look like an inverted parabola like this, with a line diagonal. Am I right?
What's wrong?
What? You got minus 4 on the end. But you got the blue box on the board. So I think Enrique, I saw his, right? Enrique looked like this. This part came around like that. Like this something?
You been where? With who?
Okay? It should look like that. If it doesn't, please raise your hand so I can see, so I can help you. But this is what you should have. And notice for this graph, only one end follows the asymptote. Right? The other end just goes down like this. But this end follows the asymptote here. So this tells us that it goes to negative infinity. It's like having a negative a value. It's like a parabola that's inverted. So like negative x squared or something, that's really like it really comes about from the original function, but for now I'm going to leave it like that. Now, let me explain to you guys real quick why the remainder means nothing. Here's why. We're trying to find the end behavior. So we're trying to find out about the function when x goes to infinity. Take a look at your remainder. In your mind, plug in infinity here. This becomes 81 over infinity minus 5. Everybody see that? Again, if I plug infinity into my remainder, this becomes 81 over the quantity infinity minus 5. 5 is, what do we call it? Useless. What's the word we're going to use? Insignificant, irrelevant, negligible. Any of those words are good.
It's gonna be 0.
I spell insignificant.
Insignificant.
I know you're mad, teacher. I'm sorry. I just want to know. It's significant.
Yeah, height.
Any of those words are fine.
So we can't win.
Any of those 3 words are fine. Insignificant, irrelevant, negligible. Now, Rosie already picked up on it, but take a look here. The 5 drops off, I'm left with 81 over infinity. But what did we say a minute ago? When you divide by infinity, it's really just 0. So this remainder is pretty much 0. That's why we ignore it. It has no effect on the problem.
All the time?
Whenever we do this process with slant asymptotes, the remainder just becomes ignored.
I guess.
Okay? One more.
Now you actually pass the ball.
Try this one, please.
It's gonna be a lot more ball movement.
Anybody that wants to do a bracket tournament, by the way, for the NCAA, I'm doing it again this year. During lunch today, if you want to fill them out, I'll be there.
I feel mine out.
Last year I did a school-wide bracket tournament for the March Madness to see what student win. I did like a gift card as a prize.
Wait, what bracket?
During lunch today, you can see they're all there.
If you win, what would you
Calculation
get?
process?
I gave like first and second prizes, or first, second, and third last year. Yeah.
What did you get?
I forget last year. I think it was a teacher that actually won it.
What did you
Mr.
get?
Wood?
I gave like a gift card, like a $20 gift card for something. Yeah. So during lunch today, it starts today though, guys.
No, I know
The
the
tournament
map.
actually starts today.
Yeah, I know. Belmont and Georgetown play.
So during lunch, I need you to fill it out if you'd like to. It's all at lunch time. Encourage your classmates if they want to too. Okay, it's just a bracket tournament. You tell me 20 teams.
D-U-D-D-D-D.
Or you need a 0 placeholder. And then guys, don't forget the 0 placeholder. There's no X term in the numerator. So when you use synthetic table, it should be 204. 204.
Yo recuerdo.
I know. Put that down for you.
Se callas, animal. Esa chica acaba con La negra tiene.
If you need help, ask the classmate how to fill out the bracket during lunch, okay?
So it's 3 times, negative 3 times 2 plus 0.
Yes. Please, guys, please don't forget that 0. If you don't have that 0, it's not going to work.
Are you dividing this time or you doing multiply?
When I do this now,
Yeah, I think I heard earlier you said synthesis division.
this is called synthetic division, but when we do this, we multiply and add, multiply and add.
I mean, I know the same, I just thought you said.
The process is division.
Esa chica te va comparando.
You got that 201? You got 201?
Nope, nope.
You look good.
Thank you, Jose.
You got 201?
Everybody got 201.
Girl,
It's on the board.
Ya te ves, yeah.
see, he didn't get 201. Look at you.
That's what I got. Does that make sense?
Oh, I didn't check that.
I get it.
I got that.
Check your numbers.
I got that.
Negative 6 and 0 is negative 6.
It's gonna be like
18
this.
and 4.
Girl, you look good.
So you're graphing that, and you're graphing this. The circle and the square and the box. Graph those two things. That's exactly right. And Zoom 6. Make sure you're on Zoom 6 this time. Zoom 6 it.
You talking about Canada?
Can do it. Come here, girl. Right away. Look, come here.
You know what? Yeah, it's a lot of Spanish.
Once you hit Zoom 6,
No.
Yeah, you do, I guess.
please draw a sketch of this in your notes. Don't just draw it for no reason. Don't just graph it for no reason. Draw a sketch in your notes, please. If you zoom out, you'll see this bottom piece, everybody. Take a look here. If you have it on a normal zoom, if you just zoom 6, you're going to see the slant asymptote and the top part here, okay? Zoom out once, and you'll see this bottom part here. Okay? Again, the bottom part only shows up if you zoom out. Or change your Y-min. Change your Y-min to like negative 30. Go to window and change your Y-min. Put you there. 6.
Tell me, see, I'm trying to get tagged. What you know? What you know? I know you're not with me. You right.
El carajo no está
That's right, man.
Did you get this?
Ay, no mames.
What?
No.
So here's what you're doing this weekend, people. On? What? Somebody show me that. That's the 44 homework worksheet. I need to see this round something. 44, Andy.
That video was like
Somebody in the general vicinity. Who's got their 44 worksheet? Thank you. All right. For concept 44, I would like you guys to do, you did 1 and 6 the other day. Work on 2, 3, and 5. Don't do 4. Okay, please write that down. Just do 2, 3, and 5. Yes, wise guy. Do 2, 3, 4. You already did 1 and 6. If you didn't do them, go ahead and do them over the weekend also. But you don't need to do number 4 for this one. And you don't need to do number 4 for this one. What I would also like you to do this weekend, please listen. Read concept 43 notes over. Make sure that all makes sense because tomorrow, on Tuesday, next week is a crazy week, guys.
Yeah.
Monday and Friday you work. Wednesday is a field trip. We have 2 days of class. Tuesday we're going to pick up right where we left off. So you have to be in here ready to go. So go over concept 43 notes. This has to do with vertical asymptote, pole, discontinuity. Okay, and then go over your 44 notes, which is what you're doing today. Where we have horizontal asymptote and a slant asymptote. Those are things you want to be reviewing this weekend, please. Okay, please review all of those things.
So wait,
We got 5 days.
We got to graph these too?
For all of these, guys, show a sketch from your calculator like you just did in your notes. Just like a minute ago, see how I graphed that? I just graphed it on my calculator afterward. I want you to do the same thing. When you get the horizontal asymptote, graph it with it. For example,
Let me do synthetic table and all that.
for this one here, when you graph the y equals x plus 2, please show this actual graph here. Use your synthetic table. Remember, guys, we're not just doing the synthetic table one today, we're also doing the one where the denominator is less than the numerator. Or the numerator, sorry, is less than the denominator, which is what we started with. There are 3 scenarios. Make sure you know all 3, and you're familiar with when you're going to use all 3. Okay, know which one is which when you're doing your homework.